So, in the last module, Professor Prabhu covered this example where a lot of understanding got developed on use of non-dimensional numbers and how experiments using one fluid could be used to scale up to other fluids just by using these non-dimensional parameters. So, you would have studied this as part of fluid mechanics also, but this is applicable in heat transfer, and this kind of concept that is ingrained because of this is very important, very powerful in real life applications. So, we will just move on to the next one. So, whatever is being told in the similarity analysis in the non-dimensional part, we are just putting it in the form of a few slides. So, in general, if I say non-dimensional velocity u star is just a function of the x star, y star and Re local Reynolds number. So, for example, if I am talking of a flat plate, so this is just to put things together. So, this is my y axis, this is my x axis, this is my u infinity. The velocity is a function of x comma y. So, this is my local location. U is a function of x comma y. So, the wall shear stress is a function. Wall shear stress is typically at a location. Okay, coefficient of friction is at a location. So, once I fix the location, the x dependency also goes away. And when you are non-dimensionalizing, so we have this x star, u star, etc., which is basically x divided by L. See, so if I fix a location, it means I am fixing the non-dimensional location also. If I am fixing u star, it is this non-dimensional velocity. So what this thing tells is a non-dimensional velocity is a function of the local coordinates, which is non-dimensionalized. So x star, y star and the local Reynolds number. Right? Why? Because Reynolds number is going to vary with a particular x location. Okay? So, it is a function of that. Wall shear stress is nothing but mu du by dy evaluated at y equal to 0, which means you are fixing a y location, which means if this is the flat plate, the shear stress is at a particular location, which is at the wall, so y is 0, but it will change with respect to x. So, the y dependency is lost, so its tau is just a function of x star and Re local Reynolds number. This should be a local Reynolds number, not Rel. Please make that correction. It is a local Reynolds number, Re subscript x. Okay, so whatever is the subscript for coefficient of friction, that would be the subscript for Reynolds number. Please keep this in mind. In fluid mechanics also we would have studied this. So, local coefficient of friction and average coefficient of friction. Local quantities means at a location. Average quantities means over a location. Over a region, sorry, it's over a region. So, if I am calling for coefficient of friction or drag at this location x1, so I will evaluate local quantities. Heat transfer coefficient at this location, it's a local quantity. So it will have a subscript h subscript f, Nusselt number nu subscript x. In fluid mechanics, you will have local coefficient of friction, you would have tau wall at that location. Right? Now, if I want to evaluate what is the drag over this entire region, then we know that the local quantities, say for example, Cfx is varying this way. So, this is the local value, the average is basically obtained by integration. So, Cfx as a function of x is this way, this is my x1 location. I would use this number for the local calculations. I will use the average coefficient of friction, which is obtained by integration of this curve, to calculate the drag over the entire length. So, Cf x bar, this bar would represent the average. So, this is 1 over x, 0 to x, Cf of x dx. This x could be a number which is say L by 3, L by 4, whatever. I am using this need not be treated as a variable. You can say this is a constant value over which you want constant value over which average is needed. So these two will be the same quantity. Okay, I'm sure this is quite clear to all of you. So same thing is what is done in heat transfer, and that's what is exemplified by this slide. So this has to be a local Reynolds number. Please keep that in mind. And of course, the definition of CFX we know is wall shear stress divided by 1/2 rho u infinity square, which when you simplify is going to give me 2 over REL times some other function of X star and local Reynolds number. That means this quantity, local coefficient of friction, is just the function of a non-dimensional location and a non-dimensional quantity, which is the Reynolds number. So for a given geometry can be expressed in terms of the local Reynolds number. If this is L, CFL, then you would be the total Reynolds number instead of being expressed in terms of the individual quantity. Okay, so this is extremely significant. Gives us the use of non-dimensional equations. Similarly, now this is the new part from heat transfer point of view. So if I am talking of local heat transfer coefficient, the non-dimensional quantity associated with local heat heat transfer coefficient is the Nusselt number. So this H would have an H subscript X. So if temperature local, so I'll just go back to my slide. So if this is my thermal boundary layer which is going to be formed, this is my delta T, this is U infinity comma T infinity, and this is my local wall temperature T wall. So if I were to draw the temperature profile at a given location, T wall greater than T infinity, so this is the temperature profile, a local value T of X comma Y. This is my local temperature, and that is a function of many quantities. So it's a function of the non-dimensional distance coordinates X and Y, the local Reynolds number and the local Prandtl number. Please remember this is Re subscript X, not Re subscript L. So when I write H, which is again a local quantity, this is minus K dt by dy. So let's go to the next slide. So H, local H is equal to minus K dt by dy at y equal to 0 divided by some delta T. This is a local quantity. Okay, this local quantity is what we are trying to calculate, and then when you do the non-dimensionalization of it, you get this as K by L into dt star by dy star at y star equal to 0. Y star equal to 0 is the non-dimensional location which corresponds to y equal to 0, which is the wall. So there also in the previous slide it was y equal to 0 for wall shear stress, which is y star equal to 0. Here also you see the same thing, dt star by dy star, which is the non-dimensional temperature gradient. Okay, and when you bring this H, L by K together, you get this Nusselt number, which is the Nusselt number, which is a function of X star, which is a local location, Re and Pr. In general, local Nusselt number would be a function of Hx by K, which means this would be Rex instead of Rel. So I would have average and Nusselt and local Nusselt number. Nusselt number is equivalent to the dimensional temperature gradient at the surface, and that is properly referred to as the dimensionless heat transfer coefficient. CFX is dimensionless wall shear stress. Go back here. CFX is your dimensionless wall shear stress. Your Nusselt number is a dimensionless heat transfer coefficient. So this part is very significant, because when you look at these two equations, okay, this is just a function of X star and Re, local location and local Reynolds number. This is a function of local location, local Reynolds number and the Prandtl number of the fluid. Okay, so I hope I am clear in this part. We have it as a function of NUX is a function of local quantity Rex and PR. there Cfx was a function of x star and Rex. So, and both of them, this is du star by dy star at y equal to 0 or y star equal to 0. This is coming from dt star by dy star at y star equal to 0. These two are going to feed into my definition of Cfx and Nusselt number. Gradients of the non-dimensional velocity at the wall, gradient of the non-dimensional temperature at the wall, and these are both identical functions except that in one you have Prandtl number. So that's what we are going to see here. So the graph is essentially showing what we are talking of as non-dimensional temperature gradient. So this is going from 0 to maximum value depending on how you have defined it there. And if you look at this, common form of Nusselt number, this was shown to you also, is going to be C into Re to the power MPR to the power N. So whatever, please remember, whatever is the subscript here, if I have local, that means I will have a subscript X. If I have average, I would have average over that length, that region. So you would have a bar and the subscript. So over bar would indicate average, subscript would indicate up to which location you are having. So this would be the case for Rex. Therefore you would have Nusselt number X. You would have same thing Cfx. This would correspond to local heat transfer coefficient. This would correspond to local wall shear stress. If I want average values, you will do the Reynolds number over that at that location only, but you will evaluate NU bar, HX bar, CFX bar. This would be the average quantities. Okay, so this is very important. Where is it important? If I have like a heat dissipating device and there are chips which are dissipating heat on a power bank or something source. So this is chip number 1, chip number 2, chip number 3. What is the heat transfer from chip 1? That means it's a local quantity, local value. Q from chip 1 is local value. Q from chip 3 is local value. This is chip number 3. But Q over entire plate, average value. What is the Q up to chip 2? That means it includes 1 as well as 2 from this region. So this is your chip 1, chip 2, chip 3, whatever. I want the heat transfer till this location. This is the variation of H with respect to X. It's going to be an average quantity over this region. At means local, over means average. This I think you have to keep in mind. This would have been taught in fluid mechanics, but the same concept is re-emphasized in heat transfer. Okay. So all your correlations for Nusselt number would be in terms of local Reynolds number and local Prandtl number of the fluid. If it is forced convection, okay, if it is forced convection, we have seen from scaling analysis that this would be the variation. Okay, so having gone through this non-dimensionalization and seen these equations, I am going to put these two together and I want you to look at this one. If Prandtl number equal to 1, that means this quantity Prandtl number is going to be equal to 1. So the Nusselt number and CFX definitions are just a function of X star and REL, because this becomes equal to 1. I am giving an input for this, which means Nusselt number is nothing but Nusselt number is nothing but CFX into REL by 2. These two functional forms will be the same because I have chosen Prandtl number as 1. This is called as Reynolds analogy. Very, very powerful, very important. Reynolds analogy. If you go back to look at this equation, you don't have pressure gradient. That means the non-dimensional energy equation and the non-dimensional momentum equation are the same. In using boundary layer approximation, d square t by dx square also goes to 0. So your governing equations are essentially the following. u star du star by dx star plus v star du star by dy star is equal to nu d squared u star by dy star squared. Pressure gradient term I have not written. This one is dt star by dx star plus v star dt star by dy star is equal to alpha d squared t by dy star squared. This is assuming dp by dx tends to 0, Prandtl number approximately equal to 1. Then if you look at this, you had 1 by REL. Let's go back here. You had 1 by REL. Okay, I shouldn't put new, sorry. I'm sorry about this. This is completely non-dimensional, so this should be 1 over REL. 1 over REL. This is 1 over REL PR, but PR is 1, so this also is same. So if you observe this two equations, the non-dimensional governing equations for momentum, boundary layer equations, these is involving boundary layer approximation. These are non-dimensional, correct? So non-dimensional boundary layer equations are identical in form. What is my dependent variable? Independent variable x star y star. What is my dependent variable? U star here and t star here. That's all. Functional form is the same and the boundary conditions being the same. What are the boundary conditions? I'm not going to write them. Look at the boundary conditions from before. You would have at the wall no slip condition, so U star equal to 0. At the wall non-dimensional temperature is 0, so T star equal to 0, V star equal to 0 at the wall, and at infinity it's the free stream velocity, so the non-dimensional value goes to 1, the non-dimensional temperature difference also goes to 1. So identical boundary conditions, Prandtl number equal to 1 or close to 1, pressure gradient term neglected, the non-dimensional momentum and energy equations are identical. With identical boundary conditions, the solutions will be identical. That means U star will be equal to T star. I am not saying U is equal to T. Please keep this in mind. U is equal to T is wrong. U star equal to T star. That means the non-dimensional velocity profile and the non-dimensional temperature profile would be identical. Another definition which you might want to use is Stanton number, STANTON, which is nothing but local Nusselt by local Reynolds into PR. This should be everywhere REX. The slide should have REX everywhere. Please note that. So this you can write is HX by K divided by U infinity X by nu into nu over alpha. You would get this particular quantity, and expand for alpha etc. you will get h by Cp into u infinity. Okay, so this is Stanton number is Cfx by 2, which is your Reynolds analogy. For laminar flow over a flat plate, you have seen this already. This is from fluid mechanics. We also showed this by scaling analysis for local Nusselt number, and if you put these things together, you get Cfx by 2 is Stanton into PR to the power 2/3, which is nothing but the J factor or the Colbourn factor. This is just for information. Okay. So for 0.6 less than PR less than 60, that means a wide range of condition, JH is the Colbourn factor and is given by this expression. This is a point to note, is developed using relations for laminar flow over a flat plate for which the pressure gradient term is 0. Experimental studies have shown that this is also applicable for turbulent flow even in the presence of pressure gradients. For laminar flow, the analogy is not applicable unless dP by dx equal to 0. Therefore, it does not apply to laminar flow over a pipe. Why? Pipe flow inherently involves a pressure loss, right? So dP by dx is what sustains the flow in a pipe. Therefore, Reynolds analogy cannot be applied for internal flow situations. Laminar flow over a flat plate, dP star by dx star equal to 0 is necessary condition. You can use this for turbulent flow without much loss of accuracy. Okay, so we are going to go to flow over external flow over the flat plate, etc. Next, this till here we have completed the fundamentals of convection, okay, real fundamentals, the behavior, the functionalities, the non-dimensionalization, etc. Now onwards we will go to how you can use these for solving problems for external flow, flow over a flat plate, cylinder, etc., and how you can do it for internal flows.